Hi, this is John, and welcome to today's webinar on energy systems and managing costs. All of PGE's seminars and webinars are in part sponsored by the Energy Trust of Oregon and the Northwest Energy Efficiency Alliance. We work together to make sure the concepts and recommendations you learn in our events are consistent across all of our individual programs and services. Today's agenda will cover four quick topics. How is electricity measured? How do I calculate energy savings for a project? How do I do a simple project evaluation? And who do I call to get advice and help? We assume that you are a non-technical manager today, staff, or other interested business professional whose organization depends upon energy-intensive systems in a non-residential place of work, your office, campus, retail, governmental, industrial process. We also assume you desire to learn and review the fundamentals of managing electricity and other environmental resources such as natural gas, water, and even carbon footprint. In the short time available in 1 hour, we can't cover all the needed topics and concepts, but we will cover the most common questions I typically hear from our business customers. And it all begins with having the ability to calculate energy costs for equipment and systems in home office or process. So there's two main reasons why I like to start with measuring, and that is, for example, Peter Drucker's major quote, "What gets measured gets managed." And this is very true whether you're talking about 50, 60 years ago, or whether you're talking about today's modern systems. If you don't have the measurement down, it's very difficult to manage. Secondly, there's a management cycle to consider. This is one that is very common. You've been exposed to strategic energy management courses or concepts, maybe Lean and Six Sigma. There is the plan, do, check, act cycle, PDCA. And measurement is especially useful in the parts about planning and then checking after you do something. So these are two good reasons why we start with the measurement side. One of the most common ways to teach about the measurements and the units of electricity is to use the examples of water systems. Let's talk about the garden hose and the home water system in your home. If you want to take a shower and suddenly all the neighbors turn on their sprinkler systems in their lawns, you may have a low water pressure problem. In the electricity business, if suddenly you have amount of force or pressure reduced, we call that a volt. The voltage is the pressure in the system. If you don't have enough volts, you have a low voltage issue. Also at home, if you want to move a whole lot of water from one place to another, or you've got a whole lot of sprinklers in your system, you're going to need a larger pipe. The size of the pipe allows the amount of water flowing through it to be higher. And in the electricity side, larger wires carry a larger amount of electrons, and that's the mighty amp. So you might see or hear the term amp in discussions about the systems you have at your office or work. If you multiply volts times amps, so that's a lot of pressure times a lot of amps, you will get the mighty watt. And this is the term that is most important on managing energy costs and your electric bills. For single-phase residential, most commercial all have single-phase. It's volts times amps equals watts. We're also, I want you to know about a couple other concepts we won't talk about today. They're a little more advanced. If you have three-phase power, larger commercial industrial, you will have the formula volts times amps times a constant, which is the square root of 3, times something called the power factor. This power factor is usually a number that is close to 1. So volts times amps times the square root of 3 times 1 would be the formula for most customers. For a few customers with very large motor loads, you can find a power factor that is less than 1, 0.9, 0.8, 0.7. And you can see that would very quickly change the amount of watts that you get if your power factor starts dropping. The last term is the mighty ohm. There is Ohm's law, which all these formulas and terms come out of, and that's the resistance to that flow of electricity over that wire. The more resistance you have, the more volts you're going to have to push those electrons along the wire. So these are the important terms that you'll need to know for today.
Hey, John, which of these terms will a customer actually see on their bill?
Good question. You won't see the ohm. Ohms is something that electricians or electronics controls you might get into. The bills are all going to be around watts as a primary number or the primary term you're going to see. For larger customers, you will see terms such as kVAR, kVAR, which stands for A is for amps and V is for volts. And sometimes when you're discussing your system or the distribution system serving your business, you will get the discussions about volts and amps. But the bill is going to be primarily about watts. So let's talk about, we've done focus groups over the years. It's been very interesting for me to understand how our customers view the product we sell. And they look at KWH as one thing. And if we're talking about the Trailblazers basketball team, they're a member of the NBA. That's a three-letter acronym that stands for National Basketball Association. That's one single organization. But KWH is not one thing. It's really three unique concepts laminated together. And this chart shows how to break them apart and understand each piece. The first piece is the metric system. We go back to our science and classes in junior high and high school, and we know that K is 1,000, M is 6 zeros, a gigawatt would be 9 zeros. So the standard metric system is the first part of the acronym. So we're really talking about how many zeros in front of the watts do you want to include. The middle part might be W for watts, but it could also be V for volts, A for amps, O for ohms. It could be a variety of things. So sometimes you may see kW, sometimes kV. The last part of this acronym is the unit of time. The mighty H is the hours of operation. Sometimes you might see an A, which represents a complete year's worth of hours, 8,760 hours a year. That's 365 days at 24 hours a day. But most of the time you're going to see the H. So KWH is the primary term that it controls about 90% of most electric bills for our customers. So here's the basic formula. We have to have a little bit of algebra here. Watts divided by 1,000, that would get you to the kWatts, times the number of hours of use would give you kWh. This formula would calculate the energy used by any appliance or piece of equipment at your home or business operations. Quick example would be if we had 20 100-watt light bulbs, you would say that's 2,000 watts, 20 times 100. If we divide by 1,000, we get 2 kWh, kWs. If we say per hour, we would say if these 20 bulbs use 2 kWh for each hour of operation. If they're on for a whole year, you would multiply 2 kWh times 8,760 to get your grand total. So here's a audience participation. So grab those cursors, grab the, I like to use the arrow. So anywhere I click, my arrow follows along. And I would like you to try to help me answer this question. How many kilowatt hours are used by one 60-watt light bulb? It's on for 10 hours a day for the next 30 days. This is a common time frame to figure out on a monthly bill how much energy would this particular device account for when I look at my kilowatt hours. And while you're using your arrows and doing your calculations, and you can see my hint, there's the formula at the bottom, I'll tell you a little story. one bulb doesn't use a lot of electricity, but one customer I spoke with was an auto dealership. This businessman counted the number of bulbs that lit up the area inside and outside his sales lot and had about 500 of these 60-watt bulbs, which added up to 30,000 watts, or 30 kW. They were on quite a few hours each month, 360 hours a month. So at 8 cents a kilowatt hour, he was spending $864 every month for these lights. So my examples might be for small, but at most businesses, the number of lights would be substantially higher. I see we've got some answers to the question. Let's see how I applied that math. Sure enough, 60 divided by 1,000 times 10 hours for 30 days would be 300 hours. It gives me 18 kilowatt hours. So that was pretty good as a group. I'm going to erase this and ask you to do it again, because I'm going to swap out that. I'm going to try to swap it out. There it is. I'm going to swap it out for a compact fluorescent, and that compact fluorescent is 18 watts. And now redo the math and see where you end up. Use those arrows or markers again, and I'll tell you a second story of where there's a lot of light bulbs, and that is apartment complexes. We work really hard to get training to property managers of multifamily complexes. One I talked to had a 100-unit complex, pretty large, and although each one is individually measured, all the units, the landlord's electric bills included hallways, pathways, parkways, common areas, the laundry room, and those were all on the landlord's electric bill. After taking an inventory, he had over 600 light bulbs and fixtures. So this, I'm using lighting because it's fairly easy and everybody has it, but it can add up quite fast. And sure enough, it looks like you've got your calculators, and 18 divided by 1,000 times the number of hours, 5 kilowatt hours would be the amount for one of these bulbs. So you can see the number moved quite a bit from 18 down to 5. So technology and efficiency can really pay off. So here's another fun game to play. These formulas are useful not only in your business, but you might be at the movie theater and suddenly realize that they're talking about energy. So here's the answer. 1,210,000,000 watts is the answer. And I would like you to raise your hand, and before you could see me practicing, so there's me practicing raising my hand over on the right, when you think you know the question, if this is the answer. Some people get it right off the bat. Here's a hint. So there's the first hint. This is a movie. No one's raised their hand yet. Here's another hint. This is an electric vehicle. And the final hint is good old Doc Brown. And of course, his question was, where in the heck am I going to get 1.21 gigawatts, which is, if you read the label on this DeLorean time machine, the label says, I need 1.21 gigawatts in order to make my trip. Another way we could apply our formula, though, is to say, how many kilowatt hours does it take for a trip in this electric vehicle time machine? And of course, we can apply our formula. How many kilowatt hours does it take to charge this electric vehicle in 1 second? We can apply our formula. We take our watts, we divide by 1,000, times the number of hours. And in this case, 1 second would be 1/3600th of an hour. So it takes 336 kilowatt hours per trip in the time machine DeLorean from Doc Brown. If you were paying, say, residential rates of 10 cents a kilowatt hour, this vehicle is about $33.60 per trip. That is a very reasonable price, I think, for being able to travel anywhere, anytime. So sometimes when we're working in offices and buildings, we are expressing energy in terms of tons of air conditioning or horsepower, which means you may have to calculate, or someone will have to calculate the watts. And this is something very important to stay on top of. Here's an example of two 5-ton air conditioners. One has a rating, energy efficiency rating of 10. It could be a SEER, seasonal energy efficiency rating, and there may be others, but it's an efficiency rating. And in this case, 5 times 12,000 divided by 10 equals 6,000 watts would be the watt rating. Now, if you bought a more efficient unit, still 5 tons of air conditioning, but 14 EER, higher efficiency, a lot less watts. 40% more energy used if you buy the first one. This is where I like to pick on purchasing managers. If this air conditioner broke, or could be a refrigeration unit, and they came to you and said, wow, I got a great deal on a 5-ton unit, your next question should be, what is the efficiency? If they bought the cheaper unit at the lower efficiency, they just locked in 40% higher energy bills for you for the next 15 to 20 years. So definitely make friends with the purchasing agent side of the house. And get on top of the efficiency ratings of the equipment you're buying. Same thing applies to horsepower. The formula is a little bit different. In this case, we are taking 5 horsepower motor, 2 different choices. One has an 88% efficiency, the other one has 92. And if you apply the formula, you'll see that you get another significant energy difference by buying the higher efficiency unit. So the message here on this slide is, even though we're not maybe not talking about watts, tons and horsepower are important factors, especially their efficiency. So let's talk about circuits, especially the wire size. If you reduce the wire size, you can reduce the costs. In this example, a customer has a choice of buying a 60 horsepower motor that is rated at 480 volts, or a 60 horsepower motor that is rated at 240 volts. From our formula of volts times amps equals watts, they are both 48,000 watts, but one uses 100 amps while the other one takes 200. Both produce the same 60 horsepower. The message, however, is if this motor is a long distance in your building from where the service panel is, you have a long run of wire you need to pay for. And of course, the bigger amps is going to require bigger wire. Bigger wire is going to lead to higher costs. And it turns out that line losses, because even wires have a little bit of resistance, those ohms, you're going to lose power through a longer and bigger wire. So the message is, watch out for amps and wire sizes. Those can also be areas where you can reduce your energy costs. This is a nice little guideline I like. Pin it on your board, print it and put it in your wallet. A lot of people say, I need to remember this. There's step 1, 2, 3, and 4. Some people like the procedural approach. Or there's the algebra approach at the bottom, watts divided by 1,000 times hours times the price. I like the step-by-step procedure. It's kind of universal. Find the W, then do the K, then the hour, then the price. And you can calculate the energy cost of any piece of equipment. So here's a math example. Get your calculators out and your little arrows or markers to help me answer this question. What are the power costs of lighting an office for a month? Each area, this area has 40 fixtures in it. There are 2 lamps, 45 watts each, so a fixture uses 90 watts, 10 hours a day, 7 days a week, 8 cents per kilowatt hour, assume 30 days in the month. So while you're doing that, I've got another fun little customer story. Nope, I guess I don't at this point. I did have someone tell me the other day that they, as a customer, they felt like they were a crime scene investigator, like a CSI Las Vegas TV show. In life is kind of like word problems, and you may or may not have all the information you need, and that's certainly true with managing energy. Quite often you're asking more questions than you're getting answers, and having to be the investigator. Well, it looks like we have several different kinds of answers here. Let's see how I did the math here. So I said that the watts were 40 fixtures at 90 watts each. So there's my wattage. I divide by 1,000. My hours are 10 hours a day for the full 30-day period. So it's 300 hours again. At 8 cents gives me 86.40. So I'll lead you through another example. In this case, it is a purchase of an air conditioning unit, and we're back to that efficiency difference. And we're going to start to get into project evaluation. How do you make a decision? And payback period is very important. Yes, Beth?
Hi, John. It looks like Manny Obi has a question. I'll unmute him.
Hi, Manny.
Manny, are you calling user number 2 or calling user number 5?
Oh.
Hi.
Hello.
Yeah, on slide 410, I think it's kind of tricky there. You go like 7 days, then 30 days. So,
yes, it is tricky, and I at first was going to simplify that, and I decided to leave it in there because the message is it is a word problem, and you need to write it down like I did with the formula to really get it straight. Is how many hours are these lights on? They are on 7 days a week, which means they're on every day, and it's a 30-day period. So the 7 days in this particular case, you really don't need to know if you assume the lights are on every day for 30 days. Is that what you were speaking to?
Yeah.
Yeah. If somebody had said it's 10 hours a day for 5 days a week and assume 30 days in a month, then it would make a difference, wouldn't it? It would be only 5 days a week. So it is a little tricky, and I decided to leave it that way. A lot of times you have to figure out what information don't I need versus what I do need.
Thanks, John. I'll go ahead and mute Manny if that's the last question.
Well, Manny's exactly right. It's a tricky one. So let's talk about our payback period on slide 15. The customer has a choice between 2 air conditioners. One is more efficient, so it only uses 1,000 watts. The less efficient one uses 1,200. They both produce the same amount of air conditioning. But of course, the one that uses less energy is going to cost you $100 more. The most common rule of thumb in making decisions or assessing equipment choices is the payback period. So in this case, I said the air conditioners use 6 hours a day for 4 months, again, using the 30 days a month, and I've said 6 hours a day, meaning every day. The cost is 10 cents. I like 10 cents simply because it's easy to do the math. How many years will it take to pay back the $100? So in this case, find the W is the choice between these 2 machines is the 1,200 watts minus the 1,000. I'm getting a 200 watt savings. I'm dividing that wattage by 1,000 to get 0.2 kW. My hours are the 4 months times the 30 days. It's on every day. times the 6 hours a day, I get 720 hours. The energy bill savings then would be 0.2 kW times 720 times 10 cents, $14.40 saved per year. If I then divide that into the $100 to see how long before I get my $100 back, the answer is about 6.9. So it will take about 7 years to pay back the $100. The most common rule of thumb I've heard from my customers that I've talked to over the years has been 3 years, sometimes as long as 5, and sometimes as short as 12 months or 18 months. If you're in the restaurant industry, it's probably going to be a lot shorter term than if you're in an industry that's been ongoing for 10, 15, 20, 30 years. Or if you're a school district, you can think longer term. So the payback period tolerance, what your decision rules are, has a lot to do with your industry or your business. And here's where the role of the Energy Trust and utilities, the state tax credits, federal tax credits, they really want you to make the choice of getting the more efficient unit. So what they're going to do is they're going to give you a rebate, an incentive, a tax credit, something that lowers that first cost. Now when we rerun the formula, we have $100 minus the 50 divided by the annual savings, and I get 3.5 years payback. This is much closer to most businesses' decision rules about requesting funding for a change out or purchasing a better piece of equipment. In our company, it's 5 years. We've been around 125 years, so if it's a 5-year payback or less, it's usually worth filling out all the paperwork. In most other businesses, it's going to be 3 years is the most I've heard, most common I've heard. Let's talk about another example. This was one that I actually observed in a store. 2 bulbs were both the same exact wattage. One was at $4 and one was for $5. There was a $1 difference. And I thought, well, that's easy. I'll choose the $4 bulb. It's the same light, same amount of watt rating, same lumens. And then I noticed by reading the labels, oh, one is 8,000 hours of life and the other one is 12,000 hours of life. Now, if you were purchasing 100 of these for a business, you'd want to know, how do I make the decision here? What's going on? What's the math? So I'd like you to do a quick reaction. Mark which one of these do you think you would make in your business. If you're a shorter term, a longer term business, what do you think would be the typical decision that your purchasing might do? I see someone has marked the $5 bulb. That's a good long-term investment. Let's look at how I answered this question. And there are other approaches. This is the one that I looked at. If you buy the $4 bulb that lasts 8,000 hours, I made an assumption of how many hours a year the bulbs are used. So let's say it's 10 hours a day and it's on every day for 365 days a year. That'd be 3,650 hours per year. If you divide the 8,000 by that number, it tells you these bulbs on average, some more, some less, will last about 2.2 years. If you buy the $5 bulb and put it in the same spot for 10 hours a day, it's going to last 3.3 years. So you get over an extra year of lighting for $1. If you look at 6.6 years from now, you would have had to buy the $400 bulbs 3 times for 3 replacements, but only 2 times for the $5 bulb. So 3 times 400 is $1,200, 2 times 500 is $1,000. You save $200 by buying the $4 bulb in the long run. There's a couple of other things that customers have pointed out to me regarding benefits beyond just the dollar savings. One is a customer pointed out to me or reminded me that the commercial industrial sectors have to recycle compact fluorescents. It's required by law, and that in this particular case that recycling usually costs them something. In this case, they postponed that recycling cost by up to a year longer, and also they skipped the whole recycling year in the 6.6 years. So recycling costs were reduced, and if you went back to the payback period calculation, you could actually say, you know, that's even more of a benefit than just the energy savings on the bill. The other one that was reminded to me was that the labor to replace the bulbs is also a cost that is reduced here. Again, a whole year going without having to replace these bulbs compared to 2.2 years for the others. So labor savings in replacements and recycling costs are two very good extra benefits by looking at the life of the bulb. Lastly, I'd like to talk about load shape. Load shape is a very powerful term. You may hear about it whether you're on the utility side talking about service or whether you're talking about on the customer side and looking at an energy management system. This first slide around shape really helps you understand or ask great questions. This is looking at just monthly bills, and there's 4 years worth of bills here. And what I've done is to place the winter in the middle, because that's where the peak months were. So obviously this particular load profile is looking at something that peaks in the winter. Could be an apartment, could be something that has a whole lot of heating and people in it. And what you've got is 2 winters that are 2003 through 2005 that are up here for the winters. And then the other 2 winters are 2005 through 2007 are down here. And that's a pretty big difference in winter bills. And what I like about this is it graphically shows the savings. All this in here went away between the 2 winters before and the 2 winters after. Something happened in this complex. I asked the customer what was going on, and they said they upgraded some very efficient HVAC equipment, but were surprised that it was up to a 40% difference in the heating costs by going from a higher efficiency unit and spending a little more money. So here's a way to graphically represent the before and the after of a particular decision. If you have these kinds of pictures, you can then go to your management and go, I can do this again, and this can be used to fund future projects. It gives you some credibility. Of course, if you make the change and it doesn't show a change on this chart, then it leads to other great questions. Why wasn't there a change? In some cases, it's, well, we put in the more efficient equipment, but we doubled the hours of operation. So your shape would look pretty much the way it looked before. So shape is really good even on a monthly bill analysis. If we look at the shape of what they call interval data, here's an example of a customer who has an energy management system that measures every hour. In fact, I think it's every half hour. And they've taken a 24-hour clock. So we've got noon here in the middle, and then we've got midnight out here at the ends. And we've mapped 30 days of billing cycle on this chart. And at first I thought, well, that's pretty complex. And then they showed me, well, this is a school, and so Mondays, all the Mondays through Fridays kind of fall right on top of each other. And I went, okay, I get that shape. By 8 o'clock, everybody's there, and by 3 o'clock, everybody's starting to leave. And then they said there are these other times down here of there's 4 Saturdays that are kind of right in here, and there are for Sundays, 4 or 5 Sundays right in here. And now with this chart, you can ask some very interesting questions. And this is an actual example. The first one was, what happens every night around, looks like 1 to 1:30 at night? Something comes on and stays on until everybody comes in. For a long time, they couldn't figure out what that was. Finally, someone in the IT department said, that's a piece of software I bought that turns on all the computers and backs up all the data. The facilities manager said, great, how long does that take? And they said, less than an hour. And he said, well, why does it stay on all night? And the answer was, well, the software, you got a special deal. It can turn them on, but it doesn't know how to turn them off. So the facilities manager said, I'll buy you the better software. And so now this shape changed, and he saved all this energy down here every day for 365 days a year. It added up to be a pretty big number, and it paid for whatever software upgrade that had to happen in the IT department. So that was a really good result from asking that question. The next one they asked was, why does it take so long for the load to drop off? If this is a school, it's empty fairly quickly. And they couldn't figure it out, and they finally found that the janitorial service was turning the lights on in all the rooms, and then as they cleaned a room, they would turn the lights off. That way they knew what rooms they had cleaned and what rooms they hadn't. Well, obviously, this takes quite a while before finally they leave and all the rooms are clean. So the facilities manager negotiated a revised maintenance contract, and now the shape would start to look like this. It would go down fairly quickly, and they saved all that energy in here. So again, shape led to a change in process that resulted in energy savings. And again, this is Mondays through Fridays. The final one was the most interesting. They couldn't figure out why Sundays were higher than Saturdays. Finally, they figured out that to raise some extra revenues for the school district, they were renting out the facility on Sundays for a church group. Well, now they knew exactly why that shape was there, and they could measure how much are you charging them to rent the building, because it better darn sure exceed the cost of the energy being used. So now they had a way to measure exactly what should the charge be to more than cover the cost of the energy as well as cleaning and the other things. So it didn't change the shape, but they now had a revenue to cover that cost that didn't pertain to the rest of the school days. So those were 3 really good results. 2 of them actually changed the shape. The running all night, they had to purchase a piece of software. The janitors, they simply had to change their behavior. And from the Saturdays and Sundays, they simply had to charge enough money to make sure they were paying their fair share of the energy costs. So those are 3 really good examples of measuring, monitoring, calculating, and visually seeing what's going on rather than a spreadsheet that would show every hour over a 30-day period. That would be not very communicative until you could map it. So I'm often asked, well, okay, you got me interested, where do I start? And as you saw from the chart and the rest of my examples, these are the 3 areas that I would say, if as a management, I would write a short initiative around. Are there things where you can change the behavior, change the culture? Conservation means don't waste it. Put signs up that say, when you leave, turn off this switch. I had one manager tell me stories about he would calculate the kWh per hour and put it near every switch so that people knew, wow, I need to turn this off because every hour it's on, it uses a lot of energy. The maintenance of equipment can absolutely affect efficiency. If you see your costs slowly going up for a particular piece of equipment, perhaps maintenance of the equipment, something as simple as changing filters more often to get airflow through an HVAC system, can definitely have an effect and show shape changes on energy bills. So changing behavior is an easy way to get started. Second one is change the process. Improving the operating procedures and processes can gain efficiency, reduce costs, monitor, detect unexpected conditions. The two examples there that we've talked about is changing the process around the auditors. Didn't require equipment changes, simply changing the formal procedures. Regarding the unexpected conditions, a lot of EMS systems, energy management systems today, can actually use mobile devices. You can set limits of any time my kWh goes above a certain level for a certain hour or a certain time of day, send you a text, send you an email, set off an alarm on a computer. So you can set conditions, expected conditions, and have the system tell you when it's out of the range that you're expecting. So those are good, change the processes. And finally, change the equipment. We talked about that purchasing decision, replace the equipment with higher efficiency. I had one customer tell me, gee, things seem to always break in the middle of the night or on a weekend when no one's around. And of course, if it's refrigeration, you have to get it replaced very quickly, and there's no time to go through a purchasing decision. You simply go out and get the whatever unit you can that meets the requirements, and you install it and get the operations back running. Well, the manager decided that he would put a label on every piece of equipment that was high use, and it was the specifications for when this breaks, replace it with the following criteria. And he set the efficiency rating. He set the life on it, not just the wattage that had to have to get the job done. And he found that that was a very good way to, A, make sure he didn't get a low efficiency piece of equipment that he was stuck with for 15 years, and two, it also helped change the behavior. People started to ask, oh, that's an important decision about the efficiency. It's an important decision about the life of the unit. So that has a twofer for it by putting the labels on it and letting everybody know that's what the labels are there for. So that's kind of my three places or three initiatives that I might start at a place of business. So what are your next steps? I get that asked a lot. I would immediately establish a management feedback process. Start measuring, start monitoring, start graphing, start figuring out what's on what circuit. There's a lot of crime scene investigator type thinking to get a handle on it. Compare your energy use with some kind of benchmark. This Monday versus last Monday, this month versus the same month last year. Find industry standards of how many kilowatt hours per square foot you should be using in your office building. Get a baseline, get a benchmark, and compare against it. Develop and maintain a list of project ideas. We saw that the payback period was significantly influenced by the incentives that are available. And those incentives can come and go. They can be there for 6 months, or they can be retired at the end of a year and suddenly not be available. So even though a project doesn't pencil out, I would keep that on a list. Keep checking on the prices, keep checking on incentives. It may turn into a yes at some time in the future. And finally, I would say keep learning. Keep attending these kinds of seminars as refreshers or learning. Stay abreast of changing technology, energy prices. It just doesn't ever disappoint me to advise customers to keep learning and stay abreast. It will pay off. So the last piece that we said we'd talk about today is who to call for help. Here's two names for you, Paula Conway at Portland General Electric and Darren Spencer at Portland General Electric. Paula handles kind of the commercial side, and Darryl the industrial process and agricultural process customers. They are surrounded by a whole floor of specialists, lighting specialists, LEED certified specialists, industrial engineers, civil engineers, mechanical engineers, just a lot of really good, talented people. And they have a lot of counterparts over at the Energy Trust of Oregon. NEA has some good programs. They have people, and they know where free services are for helping you figure out your energy needs. So with that, I think I will turn it back to Beth and see if we have a couple of questions.
Thanks, John. And before we proceed to question and answer portion of the webinar, I'd like to remind you and encourage you to either submit questions to me through chat or raise your hand and you can ask them out loud of John. That's what we're here for right now. And at this moment, I'd like to draw your attention real quickly to a poll I just opened in the lower right-hand portion of your screen. If you could take a few moments to fill this out, we would really appreciate it. We do use this information to improve future webinars. And right now, I'd like to share a next step that someone shared with the group, and that is that they would recommend the Strategic Energy Management Program through the Energy Trust for commercial and industrial customers. And that is a great program. And we also have a seminar workshop in February, end of February, the 26th, on strategic energy management and how to develop a training plan for your organization. We'll be following that up sometime in April, I believe, with a webinar. So I'd like to go straight to the first question we have, and that is, John, you mentioned talking to your purchasing managers about costs and length of use of bulbs as an example. Do you have suggestions for how to make that pitch to your purchasing manager? If they are just looking at the dollars, how can you get them to understand that it's a length of use or there are other issues involved?
That's a good question. I would say there's two things I would do. I've given you you're going to get copies of these slides with that simple one about the light bulb and the air conditioner purchase. So you can give them these simple examples and ask them, how does the purchasing criteria line up with these kinds of examples? Do you look at the life? Do you look at the efficiency ratings? And what you may find is, yes, they do, but the efficiency ratings could be higher, and so you might just have a conversation. So cup of coffee over lunch, start that conversation. Second thing you can do is we do offer, and I think we're going to offer it again this June perhaps, a seminar specifically designed to link the operating management with the financial management, like purchasing managers. And I've already gotten the agreement to get a panel of CFOs. It's called Energy Efficiency and Renewables, a CFO Perspectives. And so you can come to a training event together and have a discussion of how to apply what you're hearing at the meeting. But I can assure you, CFOs want good projects. And sometimes they are going to talk in languages well beyond just payback period. But the purchasing manager, I would take them along and come to something like that together.
Thanks, John. That's really helpful. And our next question is, where do I find the amount of watts used for a specific piece of equipment? And where can I find a list of more efficient, similar equipment when I need to replace it?
Two-part question. By federal code, there has to be a label somewhere on the equipment that tells you the wattage. It may also tell you volts and other information. Efficiency ratings, I think, have to be there for motors and HVAC equipment. So first of all, look at the labels. It sometimes is on the box, but I believe now it also has to be on the equipment itself. Secondly, I would go to the Energy Trust website or the state websites if they have tax credits, and they will tell you the criteria for the equipment and often the types of the specific names of the equipment that meet their guidelines to get incentives. I guess the third way is, if you have any questions at all, call Darren and call Paula, who have the energy experts in the office that can either look it up or guide you to something specific. But I don't know of any single spot where you can get every piece of equipment. You kind of have to ask for help and check out the Energy Trust website.
Thanks, John. That was our last question, and now we'll proceed to some information about our future seminars.